Hello everyone, welcome back. Let's wait for 5 more minutes to see if anyone joins. Then we'll start sharp at 3:05. Okay, so let's begin. This is NOC EE-62 NPTEL tutorial on basic electronics. This is more of a problem solving kind of session so that you can solve your assignment problems in due time with efficiency. The course instructor is Professor Mahesh B. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. The duration of this course is 12 weeks and we are almost at the end of the course. With this will be the 10th week, and as you know, we go live from 3 to 5 every Sunday. So 2 more weeks will be remaining after this. So some basic prerequisites, as I reiterate it every week, I expect that you all have gone through the previous week of lectures, week's lectures that were posted on the course web page, right? And also you should have tried the assignments by yourself at least once so that you can you can get something out of this kind of tutorials, right? And some basic decorums I want to follow you that please keep your microphones muted all the time. And also if you have any question, you can use the raise hand option. I will be giving you some time to ask your query after each problem or topic I discuss. And also at the end of the 2 second hour, you will be given around 10 minutes of time to ask your queries, if any, regarding the session, right? Please keep a scientific calculator handy. This will help you to solve the problem along with me during the session. Okay, so let's begin. This is 10th week. So today we will be discussing basically basics of logic gates. Okay, digital electronics basics. Most of the thing which I will be talking about today, you must have covered it in your +2 level, or at least you must have gone through the lecture material. So you should be very familiar with this. So this will be a very easy session for you probably. So let's start. So you know that we have three kind of basic gates, right? These are AND gates, OR gates, and NOT gates, right? AND gates are symbolized as this, and your output is simply A and B. This dot symbol signifies the AND. Sometimes we do not even use the dot symbol, right? And how the truth table looks like? The truth table looks like this. When both inputs are 0, your output is 0, and any of the input is 0, our output is also 0. And when both the inputs are 1, then only your output is 1, right? So this is the AND logic truth table. Similarly, you have your OR gate. Here we use the symbol plus to signify either A or B. If true, then the output will be true, right? So what is the truth table? The truth table looks like this. So when both are 0, it's 0. Else, every case, it will be 1. If any of them are 1, either A or B, then the output will be 1, right? And what about the NOT gate? NOT gate is nothing but your inverter, right? It takes one input and your output is simply, we use it this, or let's say this. Let me not say this, or this, let's say. Okay, either we use implicant sign or we use bar, right? So what is a truth table? Truth table is something like this. It just inverts the signal, right? So these are the basic three gates. We can build any digital circuits, be it combinational and sequential. With combinational and sequential means your combinational input, it depends upon the current input. It does not have any memory. Sequential input depends on the previous states also, right? So any kind of digital logic, whatever you see in today's processor, everything can be built based upon these three basic gates, right? Also, we have some other special kinds of gates. You must have heard of NAND gate, right? So this would be your AND, this would be your OR, this would be your NOT. So what is a NAND gate? NAND gate is nothing but AND plus NOT, right? So the symbol is like this. You take this from the NOT and this from the AND and you make this kind of symbol, right? So this is your NOT gate. And what is the truth table look like? It is just an inverting thing of your AND gate, right? Because you are just using a NOT gate in front of your output of the AND gate. So it will be 1 and this will be 0, right? Similarly, what is this? NOT. NOT is nothing but OR plus NOT, right? And as you have rightly predicted, the symbol is something like this. So this is your A, this is your B, this is your Y, right? So what is the truth table? This also you must have guessed. This is just the inverting one of the, what I mean to say is this is just a NOT operation between this to this. Similarly, this to this, there is just a NOT operation. And also you know that NAND and NOR gates can be used to make individually, can be used individually to make a make all the basic gates. That means and or not gates, right? That means by using only NAND or NOR gates, we can make any digital circuits, right? That's why these are called universal gates. This will be very helpful when you will be designing your VLSI system design, right? In your courses like VLSI system designs, where you will be designing how these gates are made using transistors. So in those kind of courses, this will be very helpful to know that how this NOR and NAND gates are being made by the simple PMOS and NMOS circuits, right? So some more basic things before we get started, that let me tell you how an inverter circuit looks like. A, CMOS inverter. That means suppose this is your A. So here you are getting A bar, right? So how does it work basically? What is inside this block, right? Our aim is to find out what is inside this block. It is nothing but there are two transistors, right? This is your PMOS, this is your NMOS, right? These are the gates. Gates of all of them are connected. This is just grounded and this is just some supply voltage, right? This is your PMOS, this is your NMOS. Okay, this is your V input, this is your V output. Okay, this is your basic inverter blocks, right? Means when you have, what I mean to say is this entire stuff is, you can say this is the circuit basically. Okay, this is the main your inverter circuit. By the way, NOT gate is also called an inverter. Okay, so you must be asking yourself this question that why CMOS are used. One of the basic reason is no static power dissipation, right? Just you note these terms and everything, every explanation you will be getting in your higher courses. Okay, but it is good to know beforehand why, how the thing looks inside when you open it. No static power dissipation. Okay, that means when you do not have a switching of between 0 to 1 is there, then there will be no power dissipation, right? Because there will be no path from directly from supply voltage to ground. Okay, so your NAND and NAND and NOR gates can be made using this simple PMOS and NMOS blocks, right? Or I would rather say pull up network and pull down network. Okay, just remember this thing so that any logic circuit you will be making using this NMOS, this NAND and NOR gates, right? There are distinct advantages when you use NAND or NOR, but basically you must be hearing about NAND, 3D NAND flash and or something memory like that. So these all are coming from these basic things, right? So make sure that you understand these basic things very carefully so that you can build upon this, right, in the future courses. So there are two more exclusively unique gates. These are XOR operation. How the XOR operation looks like the exclusive OR. Basically, the full form is exclusive OR. Okay, the gate symbol looks like this, and we just you represent it this way. If we expand it, it becomes A B bar plus A bar B. Okay, and how the truth table looks like? The truth table looks like something like this: 0 0 0 1 1 0 1 1. So you see, when both are 0, that means it has to be 0, right? This is 0, and say B is also 0. This has to be 0, right? So when 0 and 1, so this is 0, this is 1, right? That means this term will be 0. and this is 0 means this will be 1, and this is 1. 1 1 AND means it will be 1. So this is 1. Similarly, you can verify that this will be the truth table for an XOR gate. XOR means exclusive OR. Okay. Similarly, you can have XNOR gate where you have the symbol something like this. You have a bubble at the edge. So you have something like this. Okay, the symbol is like this. Is nothing but A exclusive or B and not. Okay. So by the way, this is Y equal to AB bar. This is equal to A plus B bar. Okay. So how will the truth table look like for this case? The truth table will look like something like this. It will be just the inverting one, right? And if you expand it, we will see that how it looks like when we expand it. It will be something like this. Okay. So A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. So it will be your 1, it will be 0, 0, 1. Just the inverting operation of the XOR table. Okay. So now let me tell you some logic simplification techniques, right? This will be the most important thing you learn today. So please pay your attention. Boolean. By the way, whatever we are doing now is called Boolean algebra, right? So Boolean logic simplification methods. Okay. So let's start. Uh, First one is called identity, right? Identity. Okay. And what does it say? It says that suppose you have an input x, and if you add it to 0, it remains x. Okay. And if x is x, basically add means here or operation, right? This is now from here onwards, this will be, this you will read as or operation, right? And this you will read as and operation. Okay, so x or 0 giving you x, and x and 1 giving you x, right? This is called identity. Now next one is, it's a annihilator. You may not need to remember these properties, because when you get accustomed to this kind of things by repeatedly doing it, you will be very easily get a knack of it, how to do it, right? So x or 1 will be 1, okay, and x and 0 will be 0. By the way, how does this come about? You must have been familiar with set theory, right? You can think it like that. Suppose this is your entire sample space, okay? Now you say, or let me tell, let's say this is the entire stuff you have, entire universe, okay? Now you say you have x. So this is your 1, right? And this is your x. So now tell me, what is x plus 0? X plus 0 is nothing but, just hold on a minute. X plus 0 is nothing but this much only, right? So x plus 0 remains this. And what about x or 0, right? What about x intersection of 1? That means this thing intersection of x is nothing but x only, right? So this is how it comes about. So you can easily see, easily can other things you can easily just form a set and some circles inside that, and you can easily get how the values are coming about. Okay, how the formulas are coming about. So I am just writing down here how what are the formulas, because we will be using that in today's session repeatedly. Okay. So next property, let me write it down, is called involution. Okay. And what does involution say? Means x prime means not x not, and again if I take not, it returns me nothing but x, right? This is pretty easy to visualize. And next property I will be writing idempotent. What does it say? It says that if x or x, we get x, right? X and x will also get x, right? This is called its idempotent property. So in the same conjunction, in the same way, you can say that here 1 plus 1 or 1 means entire universe, and entire universe, if we OR it, that will give me the same thing, right? So it will be 1 only. Okay, this is an example. So don't read this plus as add or addition, just read it as OR. Okay, it will keep you help in understanding the, it will make you understand these things very clearly. So next property is your complement. Okay, and what is that property? Complement would be if x and not of x, if you add them, it will return you to 1, right? And similarly, if you x and x naught, if you add and them, it will return you to 0, because the intersection between the some space and whatever is not in that space is nothing but 0. So that is how complement property goes. So next property would be associative. Okay, and as you well know, this three property goes together. This is something which are very much used in linear systems, right? You must be aware of associative, commutative, and the other one you have rightly guessed is distributive, right? So let us see how this three property is applicable in case of Boolean algebra. Okay, so associative property means if you have this kind of thing, it is nothing but this. Okay, it doesn't matter how you associate some group of things when you are doing an OR operation. The same thing applies to AND operation also. Okay, this is called associative property. And what is commutative? That is, if you just change the order, it doesn't matter, right? So this is called commutative property. And what about distributive? Say you have this kind of stuff, right? So you will be having this. Okay. Similarly, if you have x plus y, x plus z. Okay. And in this regard, let me tell you a very special case. Special, not special case. Let me tell you, note this one because this will help. If you have x and x bar plus y, okay. So using this formula, you have x bar, x and x bar plus xy, right? X and x bar is from here, you see, it is nothing but 0. So you have simply xy, okay? Similarly, when you have x plus x bar y, you can just use this distributive property, and this, you know, is nothing but this 1, right? So 1 and something is that thing only because that is the intersection. So this will be x plus y, okay? It is very good to remember these two properties. This thing is nothing but equal to this, and this stuff is nothing but equal to this, okay? So this property is good to remember. This will save you a lot of time, okay? And what is the next property? That is absorption, okay? And that means if you have this kind of stuff, x plus y of x. So what is that? If you take your x as common, so it is a 1 plus y, right? So what is something 1 plus 1 or something is 1 or something is 1, right? Where did we see it? We have seen it here. Okay. So it will give you nothing but x. Okay. Similarly, if you have let's say x and x plus y, how will it go? You will have x plus x of y, right? So x and x is nothing but x plus x and y. So it becomes y plus 1. So that becomes x. Okay. So this is called absorption property. That means your y is getting absorbed into the entire stuff and your result is simply x only. Okay. So we have two more properties. This one is very familiar and I am sure all of you must have studied this in your +2 level. That is called De Morgan's law, right? And what does De Morgan's law say? It tells us that if you have this kind of stuff, right? xy naught, it is nothing but, that means the same symbol, it is nothing but this, right? And if you have x plus y of this will result into this. I am not showing the proof of De Morgan's law, okay? This is very simple and you can find it anywhere in the internet. and you must have done it in your plus 2 also. So this is very, very important property, okay? Very, very important. And one of the other derivative of all this kind of formulas is that consensus law, okay? This is very interesting, and this you should try to prove it. This is, proof is very simple. The consensus law says that if you have something like this plus yz, okay, this is nothing but xy plus x bar z, okay. Similarly, if you have x plus y, x bar plus z, sorry, x prime plus z, and you have y plus z, then you have this x plus y and x prime plus z, okay. uh, Let me show you one of the proof, okay. Let me show you proof of this. This is also again very important property, right? Let me just prove this one, and this you try at home. So you have xy plus x prime z plus yz, okay. What I can write, x prime z, and I can write yz, and I can have x plus x prime. Can I write this? Yes, I can, because this is nothing but 1, and to 1 something is that quantity itself, right? So if I now break it down using distributive property, so I will have xyz plus x prime yz, right? So now if I consider these two terms, this one and this one, so I take xy common, so I will get z plus 1, right? And from here, this one and this one, if I take x prime z common, I will have 1 plus y, right? So this, you know, this is nothing but 1, okay? So it will become your xy plus x prime z, okay? Hence proved, okay? So in the similar way, you can try to prove this one. Try to prove the dual. By the way, the way I am writing this kind of formulas are called, these two are called dual of each other, okay. So try to prove the dual of the consensus law shown at left, okay. So these 11 properties we will try to keep in mind while solving today's problem session, okay. So these are pretty simple. Anyhow, I will be referring back to these properties. So, but you should be able to try to prove each and every one. The names are not important. You may ignore the names, but these properties you should be able to deal with it, right? So, what did we study so far? So far we have studied what are the basic gates. So we have seen that basic gates are AND or NOT, and we have seen how the truth table looks like, and then we have told you that what is NAND and NOR gate and why these are called universal gates, right, and the truth table of those. Then we have told you something about the CMOS inverter, why do we use CMOS inverter and how the circuit looks like in terms of transistors, because we know that transistors are the basic building blocks. and you can make your this NAND and NOR gates simply by using this PMOS and NMOS configurations, right? Using proper pull up and pull down networks. By the way, this is called pull up network because it pulls up the output to VDD, and this bottom part is called pull down network. Okay, because it pulls down the this your V out to 0 through the NMOS. Okay. So next we have discussed what is your XOR gate and what is XNOR gate and how the truth table looks like. Then we were discussing about the Boolean logic simplification methods. So I have told you there are certain simplification methods you should remember. The names are not very much important, but once you understand the theorems very clearly, then you will get to know how the names have come about, right? So you see the important properties, I would say these things are very important. This distributive absorption and the derivatives, right? This note I have told you, these are very important properties. De Morgan's law you all must have been very familiar with, and this consensus law, right? These things we will use very frequently in today's session, right? There I may show you the proof again, but it is suggested that you digest these things at this stage only. Okay. And if you are watching the recorded video, I would request you to pause the video and note down the formulas and then try to prove all of them. Okay. And if you do not understand, just rewind back and check again. So now we'll be moving forward to the problem solving session. So let's see, what do we have? Okay, we have consider a logical. I think this the thing is readable, but let me just again blow it up so that you can see it. Consider the logical function x equal to certain thing p or q or not of r, entire thing and not of p or q. Okay, so they want us to get the truth table out of it. One thing you can do is that you can simply put your combinations to this expression only. Whatever is written here, you can just simply put your every 0, 0, 0, 0, 0, 0, 1, how you can put it and check what is x there is to be coming about. Other way to do it is, and the more simpler way and the most convenient way to do it is, you simplify this expression, right? In terms of sum of products or product of sum, anyone which you like, which you are to do, which you are more fluent in, right? So the way to go about solving this problem is that you use whatever we have discussed so far, right? And try to simplify the expression as simple as possible. So you see, you have this expression, right? P plus Q plus R bar and of P naught or Q, right? So if you just use your distributive property, then you have your P bar plus Q P bar plus R bar P bar plus PQ plus QQ plus R bar Q. Fine. So what is your P bar? It is nothing but 0, right? Because the intersection is 0. So this becomes 0. What is QP bar? That is nothing but QP bar. Let us have R bar P bar. And what is PQ remains PQ. What is Q and Q? Anything is having an AND operation with itself remains itself, right? And what does this property called? This property called idempotent property, right? You see, we have discussed this thing. This idempotent property, yeah, this here we have discussed this. Okay, so you have this Q and then r prime of q. Fine. Now what can you do? You take this pq to the front and wait, you can take q common, right? So you will have p prime p bar plus here p bar, here p, here 1, here r bar, right? And you have this term left, p bar, r bar. Okay. So anything is adding with 1 means it will remain 1, right? Anything or 1 remains 1. So you have p bar r bar plus q, right? So this is the simplest form you can get from this expression. So now you have to check how your thing is getting satisfied, right? So you have p, q, r, and let's say this is your x. So what are the possibilities? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I am assuming that you are able to write any kind of any number of inputs you can write in this kind of tabular form, right? This is nothing but your Boolean, this is nothing but your binary numbers, right? This is your 0, 1, 2, 3, 4, 5, 6, 7, right? 8 combinations out of 3 because it is 2 to the power 3, right? Similarly, if you have any n inputs, you will have 0 to 2 to the power n minus 1 number of values, right? So you see, if you notice carefully that you see there is a term q, there is a loose term q, right? So if your q is 1, you can blindly say that your output will be 1, right? So let us find out where the q's are 1. These are the q's where q is 1. Whatever the input is p and r, whatever that input be, if your q is 1, you can say 1 plus something will remain 1, right? So you have these combinations. This is 1, this is 1, this is 1, and this is 1, right? And what about the case when, what about this term? What about this term? When this term is 1, again your output will be 1, right? Isn't it? So if your this term is 1, when that will be happening? When your P and R both are 0, right? Then only both will be 1. See how am I telling these things? You have something like this. You have something like this. Okay? This you has to be 1. How can you make this 1? First of all, there is a AND operation. If you look at the AND truth table, see only this is 1, right? When both of the input is 1, that means your this stuff and this stuff has to be 1. So for these two stuff has to be 1, your this boxes has to be 0, right? So when your P and Q are 0, when your P and R, sorry, P and R are 0, in that case you will have 1. So when, which cases when P and R are 0? These are the two cases, right? When your P is also 0 and R is also 0. One case has been already taken care of, the other case will become this only, right? So these are the conditions when your output will be 1. This is one way to do. This will teach you how to intuitively think about it. Other way, you can just put P equal to 0, Q equal to 0, R equal to Q equal to 0, R equal to 0 and check what is X. Then again you can do 0, 0, 1 and check what will be the outcome. That way also you can do, but that will be a little time taking, but you will get the result, right? So I will suggest that at the first you try it in that way. That is very trivial. And then once you get the knack out of it, you can simply use this kind of short tricks. Okay. So we see when this will be 1, this will be 1, but both can be 1, right? When both can be 1? When P equal to 0, R equal to 0 and Q equal to 1. In that case, they all of them are 1, right? In that case, we will having 1 plus 1 equal to 1 condition. So have we covered that case? P 0, 1, 0, 1, 0? Yes, 0, 1, 0 is covered, right? So we have nothing left. Other terms will be 0. Fine. So what is my truth table look like? It is nothing but, if you see, it is 1, 0, 1, 1, 0, 0, 1, 1. Let's see. So we have 1, 0, 1, 1, 0, 0, 1, 1, right? The first one seems to be right. And what about the other one, second one is, here is a problem. 1, 0, 1, 1, 0, this is a problem. 0, 0, 1, 1, this is a problem. And in this case 1, 0, 1, 1, 0, 0, 1, 1. So these are the problems, right? So what is your right answer? Right answer would be your A. Okay. In this way you can solve this kind of problem very easily. Okay. So I am spending a little bit time to solve the problems because you should be able to get the knack of it, how to solve this kind of problems. Okay. So I think this is pretty clear. And going on to the next problem, which is the following function is which of the following functions is equivalent to the Boolean function given this. So they want us to get it simplified. How do we do it? We know all the simplification tricks, right? So suppose your A is written as W plus W bar X plus Z bar W plus W bar X. Okay. So you see this thing you can take common, right? So W plus W bar X, if you take common, so you will have 1 plus Z bar plus you have this Z. Okay. So 1 plus Z bar, what is that? 1 plus something? It is nothing but annihilator property, right? 1 plus something is 1, or 1, rather I should say 1 or something is 1. That means this is nothing but W plus W bar X plus Z. Now, do you know any kind of thing which can simplify this thing? Yes, we know. We have already covered this thing. This is the thing, right? X plus X prime Y is nothing but X plus Y. So similarly, can we do like this? This is nothing but your, let me do it again, break it down and do it for you. This is the stuff, right? And what property did I use here? I use here distributive property. Okay. And what is the distributive property? X plus YZ is nothing but X plus Y into X plus Z. This is the distributive property. Okay. So what is W plus W bar? This stuff is nothing but 1. So 1 and something is that quantity only. So here W plus X plus Z, right? This is the simplest we can get. Now do we see any option? Yes, B is the right option, right? So in this way you can use just this trivial formulas to get the solution. So let us move to the next problem. Which of the following functions is equivalent to the Boolean function of this? Again, the simplification problem. So your x is PQR, P plus Q plus R prime or bar. So you see one thing, that whenever you have this kind of complex form and you have a single implicant sign, always use De Morgan's formula. Okay, you know De Morgan's formula for two quantity. This is nothing but A bar plus B bar, right? Similarly, ABC you can write as AB bar plus C bar, right? This you take first, and then again AB bar you can write A bar plus B bar plus C bar, right? Okay. So what do you have for three quantities? A bar plus B bar plus C bar. Okay. Similarly, you have A plus B plus C bar. You can show it that it will become this. Okay. So can we use this De Morgan's law here? Yes, we can. We will have P bar plus Q bar plus R bar. Then we have this stuff, right? P bar, Q bar, R bar. Okay. Now we use the distributive property. So we have P bar into P bar, Q bar, R bar plus Q bar, P bar, Q bar, R bar plus R bar, P bar, Q bar, R bar. Okay. So what is P bar times P bar and P bar? It is nothing but P bar only. So P bar, Q bar, R bar. Again, Q bar, you will have Q bar. So I can write it in this form. Similarly, we have R bar. So we can write it as P bar, Q bar, R bar. So what will be this? This will be 3 P bar, Q bar, R bar. Is it correct? There is no 3, right? There is no 3 in Boolean configuration, because I have already told you the formula, right? This is called idempotent. When any input is odd or and to itself, it returns the same thing, right? So if I have this same stuff here, here and here, I will get simply this. Okay. Don't make that mistake to just add it. I have told it this is not an arithmetic operation, right? This is a logical operation. This plus signifies or operation, and signifies product signifies and operation. Okay. This is not arithmetic operation, so that you can write it 3 p bar q bar r bar. It will simply be p bar q bar r bar. Okay. So A will be your right option. So I think this is clear. Let's move on to the next problem. Okay. Consider a logical function. This we want y equal to 1 for this. Okay. Fine. This and y equal to 1 for this kind of combinations, and for these combinations we have don't care, and don't care means it can be either 0 or either 1. For logic simplification we will take it as what is convenient to us, right? And for all other input values, y is required to be 0. What is the minimal Boolean expression for y? Okay. How to go about it? I think you all must have studied Karnaugh map in the lecture series. and correct me if I am wrong. Then, if you have not done the Karnaugh map in the lecture series, just post a comment to the video lecture which I have uploaded, which I will be uploading, and I will explain a separate session for Karnaugh maps. Okay, I will try to cover the basics from this thing only. So, how to go about it? You have first thing is to write the truth table, because you are new right now. You are just beginning to understand this kind of topic. It is always better to write the truth table at the very first, as a very first step in this kind of questions. Either I would directly write the Karnaugh map and solve it. Okay. So you have four inputs, right? A, B, C, D, and Y is your output. So how many combinations you will be having? Four means total 2 to the power 4 outputs, right? Output combos. Sorry, not output combinations. It will have 2 to the power 4 input combinations, right? And what is the 2 to the power 4? 0, 1, 2, 2. 2 to the power 4 minus 1. That means 15. Okay. So we will write the binary form of the 4-bit binary form of the 15 numbers. So 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1. And just just to know that we do not lose track, it is my practice. So I will suggest you that you just do like this. Whenever you are covering four things, you just make a line, horizontal line, so that you can keep track of it, right? So you have then 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay. Then you have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay. Then you have 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So the practice is you make a distinction. Okay, there is no distinction, physical distinction, just for your convenience to have an account for whatever you are writing. So what will be your Y? It has been told that for 0001, this is your 1, this is your 1, this is your 1, 1001, 1011. That is 1011. These are your ones, right? Then what are the don't care conditions? 1010. These are the don't care conditions. Then 1011. 1011 already we have one, right? So we will not take it. 1110. 1110 is this one. And 1111. So these are given, right? And now what are remaining? Remaining things are zeros. Okay. 0, 0, here 1, 0, 0, 0. Okay. So this is your truth table. Now we need to get the minimum expression, minimum sum of product, right? What is the way? First to write down the Karnaugh map. How do you write down the Karnaugh map? To make a 16 square box, right? 16 small square box. By the way, you can make much more number of squares using this kind of thing. 16 small square box, right? So you have your A, B. Here you write your C, D. And how do you write the numbers? This is 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. And what are the indexes? Indexes are like this: 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. Okay. So this is how you fill out your numbers. So what are the values here? You have 0, 1, then 0, then 1. You have 0, 0, 0, 0. Then you have 0, 1, don't care, and then 1. Right? Then you have 0, 0, 0, 0, don't care, and don't care. Right? So now you need to minimize it. First, you need to minimize it in the you need to minimize it in the minimize the Boolean expression in the you see the your how is your output answers are given in the form of sum of product, right? Sum of product terms. So you need to consider ones in the K map, right? So what are your ones here? You have this, and you can see you can make this also in the same count, right? Because these are considered at the as the adjacent thing. You need to basically group. Basically, what you have grouped? You have grouped this two, and this two. Fine. Then do you have any ones left? You do not have, right? That means that's all. So what will be your final value of y? Y is true or 1 when we have this combination. So now you need to see you have two columns, right? So what are the common term? Common term is 1. 1 represents to D, right? So D will be your one of the product term, right? One element of the product term. And what is the other term? You need to see this. And what is the thing which is and what is the oh no, I have written it wrongly. This is 1 0, this is 1 1. So what is the common term here? Common term is 0, right? And what does 0 signifies? 0 signifies B of prime of B, right? So your output will be simply Y equal to B bar and D. So your D is your right option, right? So this is pretty simple method to solve this kind of problems. Okay? Just look it for a moment and let me know if you need further clarification. Okay? So if this is fine, so let's move on to the next problem. Okay. Here they have given a multiplexer. Okay. So multiplexer is nothing but a digital block. What does it do? Just let me explain. Suppose you have a block something like this. Okay. This is a 2:1 marks. So similarly, you can have 4:1 multiplexer also. Let me just for the sake of it explain it to you. 4 input, 1 output. Okay. So 4:1 marks. Okay. So let me say this is input 1, this is input 0. So what will be the number of what will be the number? These are called control, right? Or select. Control and select. So what is the number of select pins? Number of select pins is equal to nothing but log base 2 of number of input pins. Okay. So what will be the number of pins here? For 2 input, we will have log 2 base 2, right? That is nothing but 1 select pin. Say for 64 input, we have log of 64 base 2. That is nothing but log 2 base 2 to the power 6 or 6 select pins. Okay. So this is first thing. This is your Y. And what is the other important thing about multiplexers? The way it works as, example, suppose you have a 2:1 marks. By the way, marks stands for multiplexers. Okay. So let's say this is your I1, this is your I0, this is your S0. Okay, this is your Y. So how will it work? When S0 equal to 0, your output will be, or your Y will be whatever is given to the I0 input, right? And whenever S0 equal to 1, your Y will be I1. Okay. So how to write the relation? You simply make a truth table out of it. So this is your Y, this is your S, this is your I0, and let's say this is your I1. Or okay, just let me go about it like this way. S0, I0, Y0. Okay. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So when your select is 0, what will be your output? Your output will be nothing but this stuff, right? This stuff will be your output. So your output would be 0, 0, 1, 1. Okay. And what about this? When your input is 1, your output will be simply this. Okay. So it will be 0, 1, 0, 1. Whatever is at I1 pin will be at the output pin, right? So now if you make a Karnaugh map, out of it, so you have something like this. This is S0, this is I0, I1, 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1, right? So you have 0, 0, 1, 1, 0, 0, 1, 1. Then you have 0, 1, 0, 1, right? So you can simply see that you have this combination, and you have another one, this combination, right? So your y would be nothing but, what is this? This one. This one is S0 bar, and what is the common term here? 1, right? I0 plus, what is this term? This is S0, and what is the common term between this and this? Is I1. Okay, so this is what your multiplexer output of a two of your 2:1 multiplexer will look like. Okay, so the output will look like y equals to S naught bar I naught plus S naught I1. Okay, so now let us see what is the question. The question is that what is the output expression, right? You see that from the given question, we can see that your y would be nothing but x2 bar of, what is your I naught? I naught is your x1, right? Plus x2 of I1, that is your x1 bar, right? So this is nothing but your, you remember what kind of operation is this? This is nothing but your XOR operation, right? You remember? We have discussed this stuff. This is your B bar, A bar, B. This is nothing but your XOR operation, right? So this will be your answer. So C is your right answer. Okay. So this way you can solve this kind of problem. So let's move on to the next problem. For the digital circuit shown in the figure, which of the following truth table correctly describes the function y? Okay. So you see, what do we have? We have three inputs, right? We have A, we have B, we have C, and we have output Y. Okay, so let's see. So we have, let's say these are the possible combinations. So then it is nothing but a 4:1 marks. Okay, then you have 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay, so you see, when your S0 and S1 is 0 0, 0 1, 1 0 1 1, or S0 S1, S0 is C, S1 is B, right? This is your S0, this is your S1. Okay, so when these are 0, you will have your output I0 or 1. When this is the case, you have I1 or A. When this is the case, you have I2 or 0. When this is the case, you have I3 or A of A bar, right? So you see, first you notice where is your 0 0 condition. This is 0 0, this is 0 0, right? Then what is the output? Output is nothing but 1. So you write simply here 1. Next you see, you have 0 1. 0 1 means B is 1, C is 0. So B is 1 and C is 0. These are the cases. In these cases, it will be simply A. So what is A? In this case, A is 0, so it will be 0. In this case, A is 1, so this will be 1. Okay. Now, just let me go to the next one. 1 0, that means 0 1 in BC. 0 1 would be this one, 0 1 0 1. And what is 0 1? 0 1 is nothing but 0. So this will be 0, this will be 0. And the remaining stuff will be this case, right? A bar. So this is the case. So your A bar will be nothing but the inverting of this. So 0 remains 1 and 1 will be, or 0 will be 1, 1 will be 0, right? So your correct sequence would be this one, right? 1 0 0 1 1 0 1 0. So 1 0 0 1, this is not right. 1 0 1 0 1, this is also not right. So this is your 0 1 1 0 0 1 1 0 1 0. Okay, 1 0 0 1. Did I make a mistake somewhere? Your 0 0 is 1, 0 0 is 1. Your 1 0 is 0, 1 0 is A, here 0, 1 0 is A, here 1. Then your 0 1, right? 0 1 is 0, 0 1 is 0, and your 1 1, 1 1 is A bar, right? So it should be, just let me cross check with the answer. Your 1 1 0 0. B is 1, C is 0. Just let me once cross check. So this is 0 1, right? S1 is B, S0 is C. 0 0 raised to 1, 1 0 raised to 0 0 becomes 1. Just let me freshly do it, okay? So yeah, what do we have? We have the 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay. So your S0 and your S1, right? So your this is S1, this is S0, this is your Y. Okay. So your this 0 0, S1 is B, S0 is C, 0 0 0 1, 1 0 1 1. Okay. So your this becomes 0 0 BC, then it is 1. If 0 1 0 1, that means 1, that is A. If that is 1 0, then it is 0. And if it is this 1 1, then it is A bar, right? So we have this combination here and here, right? So it will be simply 1. We have this combination 0 1 of BC 0 1 0 1, right? This will have A, right? This will be 0, this will be 1. Then we have this 1 0 1 0, we have this, so we will be having 0, right? So and then we have this 1 1 1 1, we will have this, so on A bar, so 0 will be 1, 1 will be 0. So what do we have? We have 1 0 0 1 1 1 0 0. So 1 0 0 1. Okay, this and this 1 1 0 0. Yeah, 1 0 0 1 1 1 0 0. Okay, so your B is the right option. Okay, this is pretty simple. So this is the way to go about it. Okay, you just need to uh, be correct about what is your select input high and low, right? See, this is the MSB, this is the LSB. Okay, this thing you need to get straight. Okay, then moving on to the problem number 7, the inverting thing, right? Output is given, we need to find out the we need truth table is given, we need to find out how the mask is aligned. So you see, you need to first look at what is your select, right? Your select line is ABC, right? So you know that this is your select line. Okay, so your this is your S2, this is your S1, this is your S0, right? So when this is 0, now let us make groups. When this is 0, then what is the output? Okay, then when it is 1, what is the scenario? When it is 2 or 0 1 0, what is the scenario? Let's just make some colors here so that we get it very clear. Okay. Okay, so these are the 8 combinations, okay, of the select inputs. First thing, we note how y is dependent upon d. Here y is 0, right? So your I0 is 0. Here 1, irrespective of whatever your d is. So your I1 is 1. So this is I2 is, here you can see when d is 0, y is 1, right? So it is nothing but d bar. In this case, it is nothing but d. Similarly, your I4 is nothing but 1. Your I5 is nothing but d bar. I6 is nothing but 0. And your I7 is nothing but 1. Okay. So your sequence would be, first thing will be 0. Second thing is 1. Third thing is d bar. Okay. Fourth one is, means I3 is d. So I3 is d. So I4 is 1. I5 is d bar. This two. I6 is 0. So this one seems right, right? So your C is the right option. Okay. So for question number 7, let's see what is the answer. For your question number 7, the right answer is C. Okay. So this is the right answer. Okay. So let's move on to next problem. Problem number 8. Okay. So let me zoom it up. For the digital circuit shown in the figure, which of the following expressions correctly describes the function y? Okay. So this is pretty simple. So what you need to do? First you need to do is you need to see what is the input of the each gate, right? Here you can see the input is nothing but C, right? It is C, it is C. So the AND will be C and the NOT will remain C bar. Okay. And here A is coming, right? Understood? So this will be A, C bar and another another NOT. Okay. And this is nothing but your B. B is coming here directly. So what will be this? This will be A, C bar, B, your Y will be nothing but A, C bar, bar, and of B, and entire thing bar. Okay. Now we need to simplify this. Okay. How to do that? This is nothing but we use De Morgan's law. So we will have A, C bar, 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 dot plus B bar. Fine. What will be this? This not will cancel. A C bar plus B bar. Okay. So your right answer is A. Okay. This is pretty simple. You see, you just need to check what is just at the input of the gate. What is your value of this input signal? Okay. So this is how do you do it. So similar problem. So let me just copy this and blow it up a little bit. Okay. So let's start doing it. So this is A. This will be your A bar, right? This is B. This remains B. So this is A bar plus B entire bar. Okay. This is NOR gate. Similarly, here it is B bar. Here it is C bar. So it will get B bar plus C bar entire bar. Fine. And you see this is your NOR gate, right? And suppose you add another NOT gate. What will be that? This is suppose Z. Z is nothing but X plus Y bar bar, right? That is nothing but X plus Y. Okay. So this Y we can simply write the addition of this because this and this will get cancelled. Okay. So we will just remaining with a OR gate. So we will have A bar plus B bar plus B bar plus C bar bar. Okay. So now we use De Morgan's law again. So we'll have A dot B bar plus what will we have? B bar bar, that means B, and C bar bar, that is C. Okay. So we will have A B bar plus B C. Okay. So the D option seems right. Okay. And D is indeed the right answer. So this is how you simplify this kind of circuits. Okay. Again, moving forward. Okay, just let's copy it and zoom it up. Okay. So again, similar way, P is coming here, P is getting inverted here, so it is P bar. Q is inverting here, it is Q bar. Q is coming here, it is Q. So this will be P Q bar AND gate. This is nothing but P bar Q. Okay. So what is this? This is nothing but a NOR gate. So it will be P Q bar plus P bar Q and not of that. Okay. We simply know what is this. This is nothing but P XOR Q. That is nothing but P XOR Q. And we know that the nature of this is this, right? Or other way you can do it like that. If you know, do not remember the XOR gate, you just use simply De Morgan's law. That will be your P Q bar bar multiplied by P bar Q bar. That is your P bar plus Q into this will be your P plus Q bar. That will be nothing but P bar plus P bar Q bar plus PQ plus QQ bar, right? And this is 0, this is 0. So you will have PQ plus P bar Q bar. Okay. So just two more lines. So your answer would be this. Okay. This is the way you simplify this kind of problems. Okay. So now let's see in the truth table given below which of the following expression correctly describe the minimal sum of product from the product form of the logical function. Simple thing, we have been doing this for a long time. So what is the way? Simply draw the Karnaugh map. So we have four inputs. So we'll draw a 16 small square checker thing, right? And we have AB. We have here CD 0 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1, right? So what are the outputs? 1 0 1 0 1 0 1 0. Then this is covered. Then 1 0 1 1 1 0 1 1. Fine. Then everything is 0, right? So how to go about it? Again, you see that this is one cluster you can make. Another thing you can make is this. Fine. So you have two things. So your Y would be again minimal sum of product. We look for ones in K map. Okay. If it was we needed to find out product of sum, we would have looked for zeros. Then the answer would be Y bar equal to those product of sum and that inverted. Okay. So your Y would be here. You see the common terms of this column and this column is D bar. And from this and this is A bar, right? And what about these two? This will be their common. So this will be A bar B, and this is common between these two is C, right? So your answer would be A bar B C plus A bar D bar. Okay. So your right answer for 11 is A bar B C A bar D bar. Okay. C. So this is pretty simple K-map problem. So let's move on to problem number 12. Problem number 12 shows that, okay, first thing first, it is a XOR gate, right? XOR gate you all know. What is the truth table of an XOR gate? A, B and Y, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, right? This we have discussed earlier in the first or second slide. Fine. So now this is your one input. Okay. So just let me blow it up. So you see, this is your 0. This is your 1. I am taking this much. This is your 1 because this is high, right? This is your 0. This is your 1. This is your, I have a change here. So this is your 0. This is your 0. This is your 1, right? This is the impulse train or the pulse train. Rather, I would say this is the pulse train for the signal A. Okay. What is B? B is 1. It is 1. It is 0, 0, 0, 0. It is 1. It is 1, right? Because your this level is 1, this level is 0, right? This level is 1, this level is 0. I am just leveling the pulses. Okay. So you see, when your A is 0, B is 1, you see, whenever either any of A and B is 0, you have this relation, right? It will be 1. And when both are 0 or both are 1, it will have 0. So this is output, this will be 1, this will be 0, this will be 1, this will be 0, this will be 1, this will be 0, 1, 0. Okay, I think you have seen it, how to go about it. So your pulse will be something like this, right? So first you have 1, then 0, right? First you have, let's say 1. Okay, it will also not be correct. So first let's say this is 1, this is 0, then you have 1, then you have 0, then you do not have certain changes, right? So this is not a right option. Again, first thing is 1, not correct. Again, a long pulse of 1 is not correct. Let's see here. 1, 0, again 1, then 0, then 1, then 0, then 1, then 0. Okay. So C seems right. Okay. So C will be your right answer. Okay. In this manner, you can simply see, this is just to make sure you visualize the pulse trains also. Okay. These problems. But this is nothing else but to mix and match the inputs. Okay. A simple, very simple XOR gate problem. Next, moving on to problem number 13. So again, they are asking us find the logical function, minimal sum of product. So we'll be using Karnaugh map. Which of the following terms will not appear, will not appear. Okay, just let us highlight this. Will not appear in the expression. Okay, so let us try to form the Karnaugh map. Okay, so we have four inputs: A, B, C, D. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. Okay, so we have this 0 1 0 1. So 0 1 0 1 1 1 0 1 1 1 0 1. Then 0 don't care, 0 don't care, 0 don't care, 0 don't care. Then 0 don't care, 1 don't care, 0 don't care, 1 don't care. Okay, So how to go about it? First thing first, this one, can we make it a group of 16? First, we will check no. Can we make it a group of 8? No. Can we make it a group of 4? No. So, this will be one option, right? Again, this one, can we make it a group of 16? This one, no. 8, no. 4, no. 2, yes. Okay. Then what about the other stuff? Here, we can make a group like this, right? Using taking all the don't care option, or we can simply make a group here, right? Among this. Okay. So let's see what this term is contributing to. This term is contributing to this is A bar and this is A bar and the common thing is D. Okay. This is A bar D. This term is contributing. What does this term is contributing to? This is AB and what is the common? C. Okay. And what does this term is contributing to? This one. It is nothing but A bar B and here the common is C bar. Okay. And what was the other possibility of this term? This term, there will be nothing like this and there will be just simply one. So D. Okay. So these are the possible min term, these are the possible sum of products you will be having or the min terms you will be having. Okay. So what are the option? What is not present here? Let us check. This is present, A bar B C bar, ABC present, A bar D can be done, BD. So what is BD by the way? Let us find out BD. Let me use an uncommon color, maybe green. Okay. So what is BD? D is this, D is this. Okay. So this is your BD. Fine. So BD is not an option. Okay. So you see your BD is the right answer. It will not appear as a in the expression of the sum of product. So what will be your Y? You can write your Y as either ABC plus A bar B C bar plus A bar D, or you can write it as ABC if you consider the don't care conditions, C bar plus this A bar D, you can simply write it as D, right? If you consider this, but this will be your sum of product where this term doesn't appear. Okay. So this is how to go about solving this kind of problem. So again, in minimizing the logical function in the truth table, how many of the don't care conditions need to be treated as zero? So you see, if we use this expression, so what are the terms we do not need? What are the don't care conditions we do not need? We did not use this, right? This, and this we did not use. Fine. So this can be treated as zero also, right? These three don't care terms can be treated as 0, right? So your answer would be 3. How many they are asked? So 3. Look at the K map drawn on last page. Okay. So 0x 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 and 0x 1x 0x 1x. So this is how far it goes. And this is the last problem we'll discuss today. And that is in the circuit shown in the figure, which option correctly describes the logical function. First thing first, we need to, what is the first thing? Need to draw, need to find out the truth table. Okay, even without finding out the truth table, you can do it, but just for the sake of this problem, we'll do the truth table thing also. Okay, so what is this? AB. So this is A XOR B. Okay, this is A XOR, no, so this should be, just let me go on thinner version. A XOR B, because this is A, this is B, this is B, this is C. So B XOR C bar, right? And this is nothing but C. Okay. So what would be your this value? X equal to nothing but A XOR B and B this C and C. So this is nothing but A B bar plus A bar B and B C plus B bar C bar and C, right? So this should be A B bar plus A bar B, and if we multiply it, it will remain B C and it will be 0, right? Because C and C is C, C and C bar is 0. So if we again do this, so A B bar B C plus A bar B B C. This will be 0. So and this will be B. So your answer would be A bar B C. Okay. So this is the most simplified form. So what will be your A, B, C and X? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So how to go about it? You see, when these three turn, one min term is there. Min terms mean the sum, minimum sum of product. How many product terms are there? That is called min terms. Okay. So only for one case it will be 1, right? Which is the case? This is 0, this is 1, this is 1. Only at that case it will be 1. Other all cases it will be 0. Fine. So 0, 1, 1 we need to find out. So this will be only 1. Other all case the output will be 0. Fine. So we need to find out this case in the entire stuff, right? These options. So we need to find out A is 0, B is 1, C is 1. So A is 0, B is 1, A is 0, 0, B is 1 is okay. This is the thing, right? A is 0, B is 1. Okay. 0, 1, 1. Only at this place we have this 0, 1, 1. Okay. We need to see where this is only at this, if only at this place the output is 1 and elsewhere it is 0, right? And which option will be giving the us that option will be the right option, right answer. Okay, so we can see that this is the one, because in this case let me, so I can simply say that A is the right answer because this is 1 1 1, here output is 1, which is not correct, right? Because 1 1 1 is your 0. Again 1 1 1 is not correct. And where it is this is 1, this is 0, this is 1. It is 1, right? So it is also not correct. So your correct answer would be your A. Okay. So this way you can solve the problem. Fine. So this is your truth table. Fine. So that is all what I have to offer today. I think I do not have any problem, any much more problem to solve, right? In today's session. So this is how you go about solving basic, these are very basic digital circuits, right? You just need to be very careful about assigning the values, because dealing with binary numbers, there's so many similar zeros and ones, you might get confused. So you just need to do it step by step and vigilantly. Elsewhere, it is much more simpler than whatever the difficult stuffs like Smith triggers, phase shift oscillators you are doing, body plots. So body plots are pretty simple. So these things are much simpler. Okay. So if you have any question, I am open to answer. Else, I will again go through whatever we have discussed today. I can still afford 3 more minutes if you have any question. Okay, just let me go again. What we have discussed, we have started with basic gates. We have discussed and or not gates. We have also made a comment that these gates are enough to design any digital circuit. And again, making these gates, when you do go into the CMOS parlance, these are made using the simple PMOS and NMOS pull up and pull down networks, which are used to make first this NAND and NOR gates. These are called universal gates because by individually each of them can make entire stuff, right? Entire this AND OR and NOT gates can be made using this NAND and NOR gate individually. This is pretty simple, and you can try it, right? That how NAND gates can be made using this stuff. Yeah, how NAND gates can be used to make NOT, NAND, and OR gates, right? So these are called universal gates. Then we have simply briefly discussed about touch upon what is CMOS inverter and why these are used. More main reason is no static power dissipation. There are other reasons also, but most main importance why CMOS was into came in overtake has overtaken this BJT was this, there was no static power dissipation in the circuits, right? Then, and that means your when your device is off, your battery will not get drained, right? That was one of the key things which enable this handheld devices and low this devices which we need to run on one charge for an entire day, right? Then we have discussed about XOR and XNOR gates. Then we have discussed about this Boolean algebra, some identities, and how to how some of the logic simplification methods. So we have discussed around 11 things. In it can go up to hundreds and plus if you can derive one more and more. But these are the fundamental ones which you should remember. so that you can solve any circuits very pretty quickly. The most important of these are these four: distributive absorption, De Morgan's, and consensus law. So these are a little bit higher, more derived than the basic things. Okay, and you can easily visualize this using the set theory also. So then we have started with discussing how to write the truth table and how to use these formulas to simplify the Boolean expressions, right? Boolean expression simplification, again Boolean expression simplification. Then we have seen how to write a Karnaugh map and use the simplification technique. Okay. Then we have seen about mask, right? How the marks is being incorporated, and what are the purpose of select lines, what are the purpose of inputs. Okay, then how to write the truth table and how to convert the truth table into Boolean expression. Okay, then we have seen how to, if the truth table, if mask configuration is given, how to write the truth table, and we have done the other way around also. Okay, then we have seen how to get simplification by using the circuits. These were pretty simple problems. Then we have seen how to simplify the Karnaugh map again with some examples. Then we have tried to visualize how pulse trains look like in 0 and 1 form, so that you have the visibilities if this kind of questions come in the exam, so you will be very comfortable to deal with these things, right? Then we have again seen what are the minimum sum of product and how to eliminate the non-obvious options. Then we have last problem, we have seen how to simplify the circuit and again visualize it in the graph form, right? Pulse train form. Okay, so that's all for today. Thank you for joining. We'll meet next week. Okay.